The problem states a thin copper wire is oscillating on a conducting loop such that xt equals x naught 1 minus 0.5 sine omega t in a time-varying magnetic field given by B equals B naught sine t omega t into the page as shown in the figure. The total equivalent resistance of a loop in the wire is R. What is the induced current on the loop? What is the direction of this induced current at t equals 0? Plus, briefly explain your answer in terms of Lenz's law. So, the first thing we're going to do is calculate the magnetic flux. The magnetic flux is the dot product of the average magnetic field times the perpendicular area that it penetrates. So we would get B, our magnetic field. Later on we're going to replace it with B naught sine t omega t, but for now we're just write B. And then our area, L is going to be, so this is the loop. L is going to be constant. However, our x is varying, so we write dx, and we are going to be integrating from 0 to x. So 0 to x. Let me just write this over. 0 to x, and then we get B Lx as the answer for magnetic flux. Next, we are going to calculate the V Emf. So Faraday's law states that the EMF is given by the rate of change of magnetic flux. The negative comes from Lenz's law, which states that the induced EMF opposes the magnetic flux, and then we're taking the time derivative of the magnetic flux. So we're going to apply the chain rule. So that's going to be negative L B dx dt plus x dB dt. Because B and x, the magnetic field and the area change with the time. So our L is constant, so it stays out. B, okay, so then B, and then the time derivative of x, so x naught 0.5 sine omega t. The time derivative of that's going to be x naught, well, it's going to be negative x naught 0.5. So x naught and 0.5 are constants. And then sine omega t is going to be negative omega cosine omega t. So we have our negative right there, and then we're going to write omega cosine omega t. Now we're going to take the time derivative of dB. So of the magnetic field. So that's B naught sine t 2 omega t. So that would be B naught 2 omega cosine 2 omega t. Cosine 2 omega t. So that's the answer for the V Emf. Next, we're going to calculate the induced current. So induced current is equal to the V Emf over the resistance. So the V EMF, we're going to actually factor out common terms. So L omega x naught b naught. We're also going to replace the b and the x with what's stated in the problem for those variables. So then we get 0.5 sine 2 omega t cosine omega t minus 2 cosine 2 omega t multiplied by 1 minus 0.5 sine omega t. And then this is over the resistance, and the resistance for this problem is stated to be just R. Right, R. Okay, so that's the induced current for the problem, and we got that by factoring out the common terms and replacing x and b with the value stated in the problem right here. So, and then next we need to find the direction of the induced current at t equals 0. So when at the induced current at t equals 0 is equal to negative 2 L omega x naught b naught over R. We get this because when we replace t with 0, this term becomes 0. So then this term is just this term is just basically just canceled out. And then that becomes 0, and then this sign over here also becomes 0. And so we're left with just 2 cosine 2 omega t. And then the cosine of 2 omega t, so when time is 0, this becomes 1. And then we're left with negative 2 times L omega x naught b naught over R. And now, using Lenz's law, we have to explain the direction. So when time is 0, the surviving term is this term right here, 2 cosine 2 omega t. And that comes from the derivative of the B field, which is B naught sine 2 omega t. So the B field is increasing into the page. It's increasing because when time is equal to 0, cosine 2 omega t is 1. So since it's 1, it's changing faster, and that means it's increasing. So the B field is increasing into the page. And to bring a balance to the system, we want to oppose that. So the induced B field will be coming out of the page, and we'll have an induced current going in a counterclockwise direction. So the induced current is going to be counterclockwise, and yeah, that's it. So that's the answer to this problem.